Hi there, this is Lucius the Frown Boys from ENG Suite, and today we are going to start talking about analysis of variance, or ANOVA. And ANOVA is really one of the foundations of engineering, and we're about to learn why. So ANOVA is an acronym, and it stands for Analysis of Variance. And ANOVAs compare whether two or more sample means are statistically significant. But there's different kinds of ANOVA. There's a one-way or a one-factor ANOVA, which is used to determine if at least one treatment group or treatment level within a single independent variable is different from the others. A multi-factor is where we evaluate the significance of individual factors and interaction effects of those factors. So that's when there's multiple independent variables but only a single dependent variable. And there's a special example of the two-way, which is the gauge R&R. So gauge R&Rs are built off of that two-way ANOVA. Where one factor is your operators and one factor is your parts, and we look to see if there's a significant effect of different operators or different parts on the gauge, or if there's an interaction. So maybe some operators measure certain parts differently than other operators. And we'll get into all of that a little more when we get on to two-way ANOVAs and especially our gauge R&R video. So there are some assumptions of ANOVAs that we have to meet first. The first is independence of observations. So that just means that each of our measurements is independent of others. So they would be measuring different parts for the same dimension. So that would be independent observations. We're not measuring the same dimension on the same part over and over and over. The second would be normality, that the distribution of our residuals are normal. So the distribution of our measurements are normal. And the last is equality of variance of all groups. So there's a variety of ways that we can evaluate this. QE Suite gives you a couple. We give you the Bartlett's test and the Levine test and the F test. The F test is available in Excel, but it only tests between two different treatments, two different groups, whereas the Bartlett's and the Levine will both test more than just two treatment groups. So why do we use ANOVA? Well, again, ANOVA stands for Analysis of Variance. And in engineering, we're looking at how the effects of independent variables on dependent variables. So we're looking at the variance of different treatment groups, right? In manufacturing, we can say that a little bit slightly different and say that it's used to analyze the effects of process conditions on products. So we'll often use them during our process characterization or optimization activities when we want to know how do different processing parameters affect the products. So when we're doing an ANOVA, we're really talking about the ANOVA table. And there are a few important elements of an ANOVA table that we should talk about. The first is the source. And you'll see later on the next page, actually, that the ANOVA table is divided into variation sources that represent the treatments and factors, the error or the residual, and the total variation. So you'll see that each row of our ANOVA table represents a different source of variation. And each of those sources have a degrees of freedom associated with it, a sum of squares, a mean squares, an F statistic, and a p-value. So that F statistic and p-value are what we actually use to assess the significance of the effect. So let's take a look at an example of reading an ANOVA. So this here is an example of a one-way, and we'll actually do this example with this data in our video next week when we go into one-way ANOVAs. But I just kind of wanted to show you this so that you could see what an ANOVA table looks like. So in this, we have, here, let me get the laser pointer out. Okay, so in this, we see that we have the source, degrees of freedom, sum squares, mean squares, F value, and P value. And you'll see that for a one-way, no matter how many different treatment groups we have, we will only ever have between, error, and total. That's because between is, that's evaluating the variation between each treatment group. And you'll see we have degrees of freedom of 3. So we'll get into the math later, but that means that we have 4 different treatments that we're looking at. Here is our sum squares, our mean squares, and then our F and P value. And we can use an F critical value to evaluate significance, but it's probably easier to use a P value because we know for our particular example, make sure you check with your organization, but we are going to use the standard 0.05 alpha level. And so this p-value is less than that 0.05, which means that we reject the null hypothesis. Here, the null hypothesis being that all of the treatment group means are the same. So if we reject that, then we can say that a factor is showing a significant difference from the others. Further testing is required. So all that a one-way ANOVA can tell us is whether or not one or more treatment groups are significantly different than the others. Now let's take a look at a two-way ANOVA. So in this two-way ANOVA, you'll see that we have factor 1, factor 2, and interaction. Okay, so factor 1, we take a look at our p-value. It's less than our alpha of 0.05, so we reject the null hypothesis. Therefore, the effect is significant. So the effect of factor 1 is significant. There's something going on here where different levels of factor 1 change things. So like, let's pretend that that's a temperature. And let's say we find that lower temperatures lead to a maybe a higher hardness of our paint, whereas higher temperatures lead to a lower hardness of the paint after it cures. Factor 2, we see that there is no significant effect, that, well, at least we failed to reject. So at the 0.05 level, there's no significant effect. That means whatever pressure, let's pretend this is pressure, whatever pressure we're evaluating at, we're not seeing that affect the hardness of our paint. Okay, interaction. Let's talk about this one because in a two-way, we'll get into this more later. This is a big one. So we'll see here 0.81. That means we failed to reject the null hypothesis. The effect of our interaction is not significant. Now, if we were actually analyzing some data and not just using this as an example to show you what a ANOVA table looks like, we would rerun our two-way ANOVA without the interaction because this interaction effect actually does affect factor 1 and factor 2 p-values. It doesn't affect the sum squares or the mean squares, but it does affect our f and p value. We'll get into that in a couple weeks when we take on the two-way, but for now, this is an ANOVA table. This is how you read it. So you might be thinking, is a significant effect good? As engineers, we often think that significance should either be a good or a bad thing. So think about normality testing, where significance is quote-unquote bad because we fail to assume normality, which is required for capability analysis. ANOVA should not be approached with this good-bad attitude. It really depends on what we're testing. So remember, significance does not mean good or bad. Significance just means that we see a significant difference in one of our treatments. Okay, let's take a look at two examples where we can kind of, as engineers, not statisticians, as engineers, assign maybe a good or a bad, just to show you that truly it depends on the scenario. So in our first example, we're using a one-way ANOVA to test the effect that our manufacturing lines have on a dimension of our product. In this case, we don't want a significant effect. So in this particular example, this is showing an example where we're hoping that we don't find a significant effect of one of our treatments because we want each line to produce the parts the same way so that we can justify producing it on multiple lines. We want our product to come out the same whether it's on value stream 1, 2, 3, or infinity because we want, as a manufacturer, to be flexible so that we can use the flexibility of our value streams to keep up with scheduling. So that's an example that shows you why ANOVA isn't good or bad. It depends on your scenario. Example number 2. We're using a one-way ANOVA to test the effect of processing temperatures on cycle times so that we can minimize our cycle time. So we already know that our temperature doesn't affect critical dimensions. We performed an ANOVA and we said, yep, everything is statistically all right. We are just fine. So what we want to know is we want the effect of our temperature to be significant on our cycle times so that we can pick the one that reduces our cycle times. Right? So again, this is an example that shows you not good or bad. It depends on your scenario and what you're looking for. In this case, we want to reduce cycle times. So we're hoping that one of the temperatures has a significantly lower cycle time than the others. Now, let's say you're testing at your process nominal and you want this to be wider. You want your validated temperatures to be wider than your non-validated temperatures. In this scenario, you might actually switch and say, well, no, we don't want there to be a significant effect because we found a temperature that works, has a minimum cycle time. We're going to focus in a little bit on a smaller temperature range right around, let's say it's at that T3, where, maybe there's like a dip in cycle times right at that T3. And so what we want to do is we want to take T2.1 to T3.9, and we want to see no significant difference in there. So again, this is just trying to drive home that don't think of significance as pass-fail, okay? Think of it as there's an effect going on here. Our independent variable is has a significant effect on our dependent variable, and now further testing is required to figure out what that significant effect is so that we can maximize whatever it is we're trying to maximize. Okay, so in conclusion, for engineers, ANOVAs are an incredibly useful tool, and they open up the world of process optimization. They allow us to evaluate the significance of independent variables or treatments on dependent variables in our products, enabling a better understanding of how our process parameters affect final products. Again, ANOVA is one of the foundational tools of an engineer. So get used to it, get familiar, understand the math behind it, and we can really do some amazing things. So, as always, thank you so much for watching. Have a great day, and please, with your new ANOVA skills, do something awesome.